Imagine a rectangular room. It's 16 units long and 6 units wide. Now, we want to cover the whole floor with square tiles, all the same size. No cutting tiles to fit, and no gaps left over. So here's the puzzle. How big can each tile be? What's the biggest square that still fills the floor exactly? Alright, let's actually figure this out. So, how big can a square actually get in here? Well, the short side here is only 6. A square can't be any wider than that, so the biggest tile is 6 by 6. Now, how many of these actually fit along the length? 1, 2, 3. Nope, that one hangs right off the end. Way too big to fit. So we stop at 2. And that leaves this strip on the end. 6 tall, 4 wide. Here's the pattern. The length, 16, is 2 whole tiles of 6, plus the 4 left over. 16 equals 6 times 2, plus 4. Look closely at what this floor is really made of. 2 squares, and the leftover strip. The biggest tile, whatever it is, tiles this whole floor, so it tiles those 2 squares exactly. So whatever's left, the strip, has to come out perfectly tiled too. No ragged gap. Now run it backwards. Say you can tile just the strip. The strip is 6 tall, and so is each square, exactly the same height. So the very same rows carry straight across them. And a square is 6 wide as well, so they fill in completely, for free. So it works both ways. Tile the floor, and the strip comes with it. Tile the strip, and the squares come for free. Which means the biggest tile for the whole floor is exactly the biggest tile for the strip. Same puzzle, just a smaller floor. We just turned the problem into a smaller copy of itself. And that's the whole trick. Now we just do it again. The short side is 4, so the biggest square is 4 by 4. One fits. A second one runs off the end, so we stop at 1. And the leftover is a 4 by 2 strip. 6 is 4 times 1 plus 2. Same logic as before. The square comes free, so it's now a 4 by 2 problem. Smaller again. And once more, the short side is 2, so the biggest square is 2 by 2. 1, 2, and it fits perfectly. Nothing left over at all. 4 is 2 times 2 plus 0. The remainder is 0. And 0 is the finish line. The instant there's nothing left over, we're done. The last square we laid was 2 by 2, so that's our answer. Now here's the payoff. 2 by 2 solves this little 4 by 2 floor, and watch it ripple all the way back up. This 4 by 2 was the scrap the 6 by 4 left behind. Same biggest tile, so 2 by 2 has to fill the whole 6 by 4 as well. And that 6 by 4 was the scrap off the very first floor, so the same tile fills the original 16 by 6. The rest just falls into place. Every square the same 2 by 2. And there it is. 2 by 2 tiles the whole original floor. No cuts, no gaps. That's our answer. And this whole process you just walked through has a name. It's the Euclidean Algorithm, one of the oldest we know. Euclid wrote it down over 2,000 years ago, and we still lean on it all the time today. Now, that biggest tile we landed on, its size too, has a name. We call it the greatest common divisor of 16 and 6. A divisor of both, because 2 splits each side evenly, 8 tiles across the 16, and 3 up the 6, and the greatest one that does, which is just another way of saying the biggest tile that fits, the very thing we set out to find. Those 3 lines are the whole algorithm, running on 16 and 6, but nothing about it ever cared that the numbers were 16 and 6. So take any floor at all, call the long side A and the short side B, lay down the biggest squares that fit, B by B, as many as go, call that Q of them, and you're left with a strip of width R. Same as before, A is B times Q plus the leftover R. By the exact same argument as the 16 by 6, the biggest tile for the A by B floor is the one for B by R. Just like that, we've shrunk the problem to a smaller floor. In symbols, the GCD of A and B equals the GCD of B and R. And that's the whole trick. Every floor hands you a smaller floor, strictly smaller, until there's nothing left to shrink. 16 by 6, 2 squares and a leftover strip. And that leftover is the next floor down, 6 by 4. And it's leftover, smaller still, 4 by 2. And 4 by 2 fills perfectly with 2 by 2s. No leftover at all, so the chain stops right here. The square that finished it, 2 by 2. So the greatest common divisor of 16 and 6 is 2. 2,000 years old and still the one we reach for. That's the Euclidean algorithm.